Okay, but that's the web portion. Let's now actually look at the Snake core library. I think it's probably easier to start with that and then look at the command line implementation. So let's go to snake.js. So again, we've glanced into this file a tiny bit, but not too much. So I think actually there's too much code here, right? So let's start from the top. Let's just scroll through quickly first to get an idea, right? Like we have about 61 lines of code, and if you have ways of making this again more elegant and more concise, not concise as in code golf, as in just for the sake of conciseness, but as in elegance, then please do shoot something in the comments. That would be massively interesting. But what we start by doing is just requiring this base library that we've defined, again as we've talked about, with some helper methods. I'm not sure if we actually ever looked at that, but here's the base library, right? Yeah, we did quickly look at that, but we just define a few functions, such as, for example, map, and as constant, and as identity, and all of that stuff. But let's forget about that for now, right? But we load the functions from the base library, and then we do this. And this is kind of just me hacking again, so I apologize for that. But what I wanted to do is, so base, for example, exposes the function map, right? So you have base.map. But whenever I don't want to have to say base.map. I just want to be able to simply say map and refer to base.map, because they are helper functions. So, I mean, in some sense, you could argue that some of the functions defined in base here are functions that should be defined in JavaScript, if JavaScript was actually aiming to be a functional language. Like, so functions such as map or reduce are defined in the prelude of Haskell. So they're defined in the base library of Haskell. Reduce is actually called fold in Haskell. And not just that, I mean, tons of other methods, such as identity and constant and lots of other things. Some of them are not, like prop, for example, like because Haskell is a statically typed language and JavaScript is dynamically typed language. So if we look at the base library here, for example, I defined the helper method prop, which essentially takes a key and then takes an object and extracts the value under that key from that object. And that's trickier to define in a statically typed language. Actually, now that I'm thinking about it, actually it's completely definable in a statically typed language. It's just probably not as useful, right? Because you're probably using static typing because it gives you benefits. And when you're starting to use this sort of key value pair syntax, this dictionary syntax, then you are exposing yourself to runtime errors because you might end up in situations where the key doesn't exist. But anyways, that's tangential. What I wanted to say is just that in JavaScript, because of the dynamic nature of JavaScript, some of the functions that we might want to put in the base library, quotation marks, make sense to put in the base library, but might not be functions that we want to put in the base library in other languages. But anyways, this is total sidetrack. That's why I'm doing this, right? Just to expose all of those functions so I can say k and id and map and so forth, and not have to say base.map and so forth. So that's that. Okay, let's move on. Then we have these constants, right? These constants we've already talked about. We need some way of talking about the different directions. And maybe you could argue that these should be functions that, or again, like nullary functions that take no arguments and return this. But anyways, I just define them as constants. Then we have this point operation. And actually, I mean, I was thinking about this a while. Like, this is not excellent because if you could check for deep object equality, right? Like, I think in many of the JavaScript libraries you can do that, and many of the testing libraries you can do. So actually, like, object deep equals or deep equality of two objects is actually a very useful thing to have in the language. So actually, I mean, the implementation of point equals should essentially just, like if you pass point 1 and you pass point 2, then the implementation should essentially be point 1 equals point 2. If equality in JavaScript was based on the deep structure of an object and not the reference to that thing in memory, or the pointer to that thing in memory. But anyways, I mean, and even if it didn't look like this, it should perhaps be the deep equality between P1 and P2, and maybe if we do that in the curried fashion, it would look like this, right? And actually, if we have that, then point equals is essentially equal to deep equals, if you think about that, because if I put both of these at the same time, you can see, I mean, what we do is simply that we take one x here, one y here, we pass the x here, and we pass the y here. So we're just applying that function. So then it's the same thing. Like, we don't even have to take any arguments. We can make it point free. And that's the reason I'm complaining about this. Like, point equality is nothing special. Like, I want to say that the x point equals the x point and the y point equals the y point of the two things. Or not the point. I mean, the x property of point 1 equals the x property of point 2, and the y property of point 1 equals the y property of point 2. Like, that's the check I want to make. But that's just a check of equality. equality. So that's why I'm saying like that's a bit silly and that was disappointing. But I figured it was just overkill to implement deep equality, a function of deep equality in the base library. But at least now you know. Anyways, let's move on. So then we have a bunch of Boolean methods, right? So what I mean here is, I mean a bunch of functions that take some particular or potential arguments, but also the current state. And then given the current state, answers questions. So the questions that we want to have answered is whether the snake will eat upon the next update, given the current state, and whether the snake will crash given the current state in the next update. So if we have this current state and we have a list of moves, so we have a list of left, right, up, down, etc. Given the next move and the current state, will the snake crash? That's the things that we're asking here. And then this thing is, of course, as we talked about before, whether a particular move is valid. But that's before we enter the move into the state. So, I mean, maybe we could have done it in a way. We could have just blindly added moves into the state and then have a function that computes a clean state without any invalid consecutive move combinations or without any sort of inverses in the list of moves. But I chose to do it this way. Maybe the other way would have been more elegant. But so you pass a move first and then you pass a state, and then it says yes if this move is okay given this state. So if it's okay to add this move to this state. And the way we do this is just that we say, okay, well, so let's think about this. We do logical OR between this thing and between this thing, right? So let's put these like this, just temporarily so that we can think about it, right? So we're doing the same thing twice. We're saying either something holds for the x-axis or something holds for the y-axis or for the y direction. And if either of these hold, then it's a valid move. And what needs to hold is that the x velocity of the move, of the last stacked move, of the next move that we have, when we add that to the new move that we want to add, that needs to be different from 0. So what we're saying is that if we are moving in x minus 1, then if we add 1 to that, then that would give 0, because if we're moving in this direction and then we add 1, so 1 would be this direction. That would be the polar opposite of that thing, or of that direction. Similarly, if we're moving 1 and we add negative 1, we get 0, because if we're moving in this direction and we add this direction, then these cancel out and we get 0. Right? And that's the scenario that we don't want, where we're crashing into our own head. But we're saying that either the x-axis needs to be different or the y needs to be different. I mean, since you can't move diagonally, yeah, this is in some sense probably overly complicated, because clearly if the y-axis has a value, then x will be 0, and if the x-axis has a value, or if the x direction has a value, then the y will be 0. So there's probably a more simple implementation that you could look for. So let's go backwards by putting this back on one line, and then let's look at the next stuff. Actually, before we go any further, let's look at the state, right? So initial state, let's go here. I mean, we said previously that there's a function called initial state that returns the initial state that all of the other states are sort of built from. So in the initial state, we have just a few things, right? We have some number of columns and some number of rows, and these are just in order to, I mean, maybe it's not the best place to store these because they won't change, or they shouldn't change over the course of the game, but maybe if you would think in terms of levels, then maybe this could actually change, but who knows. But then we have a list of moves, and in the initial state we start with east in the list of moves. As you can see, right, like when we refresh the game, we always start from the same position here, and we always start by moving east. And that's because the default move is east, and we can't see here because the default snake is empty, but what happens after a crash is what causes the snake to start at 2-2, but we'll see that later. And then we start with the default apple actually at 16-2, so maybe that should be a random position, but for some reason I chose to put it there. So again, you can see that the apple always starts here, so we'll always automatically catch the first apple, right, by just leaving the snake to do its thing. So that's the initial state. But let's now jump back now you know sort of what that contains. And of course, the snake thing, right? Like we were saying, the snake is an array, and it is an array of positions or points, right? So things that look like this, right? That have an x coordinate and that have a y coordinate. And this is why we're saying point equal, or this is why I said point, because we call these things that have dot x and dot y, we call these points. So yeah, actually, so let me jump down. I think it's actually easier just to follow along from down here instead of going line by line, because the order wasn't superb. So let's actually just look at the next method here instead. So when we looked at the web implementation, if we go, to web.js here, you can see we talked about how we call the next function here, right? When we step the game, we say the new state is equal to the old state ran through the next function. And the question is, what does the next function do? Well, the next function is, I make use of this library method called spec, which the library Ramda, I think they call it apply spec or something like that, but I just called it spec. So you can see spec is a fairly interesting method. It has this slightly tricky implementation where it takes an object and then it takes some value and then it grabs the keys out of this object and maps over the keys, constructs a new object from that key and runs the function that hides under that key, applies that function to this x that we passed, to this value that we passed, and then it reduces over merge. So it simply merges all of these different objects that it produced into a single object. And that's a pretty complicated way of saying that essentially what we do here. Let me just, if I retype this implementation, we could retype it as that. Let's think about it. Next is a function that takes a state and returns a new object, where the new object, if I had a spread syntax, I could say is the old state, right? Plus, or actually, let's not use the spread syntax. Let's be explicit. So takes some state and returns a new object where rows is equal to state.rows, calls is equal to state.calls, moves is equal to next moves while being passed the state, and snake is next snake being passed the state, and apple is next apple being passed the state. So that's essentially what we're doing. And actually, if we would express this in function syntax as well, these first two, just to make it clear, really why we can use spec in this lower implementation, is because this is essentially then just using the prop method that we talked about before. So if I say prop here, pass row, like this, right? I pass these props as a string, and then we pass the state as the second argument. And sorry, I'm using curried or functions that allow partial applications, so we actually need to invoke the function like this. So that would be the same thing. And now if you look at that, right, if you look at that implementation, you can say, oh, okay, well actually, next is a function that takes some state, produces a new object where the state needs to be passed to all of the functions. Or rather, I should say, so next is a function that takes some state and produces a new object where this new object contains a bunch of keys. And to determine the values under all of these keys, we need to execute a few functions. But these functions, they are not nullary. We need to pass them some arguments, and the argument that we need to pass is essentially the state. Like if you line this up, you can see all of them are past the state. So essentially what we did is just that we sort of made it point free. We remove this portion. Notice how we do this. We remove this, boop, and then we say, okay, all of these need to be past state, okay? But that's why we have the spec method. So then we say spec, and then we pass state here, okay? That's also the same thing. But then we're back into the scenario that we looked at before, where it's like, well, actually, next is now a function that invokes this function spec by just passing the x that we pass it, right? Like next is a function that takes an x and runs another function through that x or over that x, and then we don't even need to specify the x. We can just remove the state here, like we remove the explicit call, and then we remove this explicit variable here, and then we just say next is the running of spec over these functions, and then we pass it some state. So I would argue that this is more clear, but I'm totally empathetic to if you have a different opinion. Like, as soon as you start to learn a few of these really common functional programming, I wouldn't say patterns, but like functions, essentially. These common functions that we tend to use all the time, like constant and id and map and reduce and pipe and compose. And I would argue for dynamic languages, this method is like super common, or this function spec or apply spec is super common. So when you start to recognize these, I actually think this becomes the easier version to read. But there's a whole discussion about whether point free is sensible or not. I can shoot some links in the description if you're interested in that. But anyways, let's move on. So that's the next method. And we've already talked about enqueue. What enqueue does is essentially that you pass it a state and you pass it a move, and if the move is valid, then you merge the move into the list of current moves that you have stacked up, right? So the reason we're stacking them up, by the way, is that if you think about it, what we can do, let me collect a few of these just to get a tail. But what we can do is that we can stack moves like this. If I just mash the buttons, now I have a tail, now I can do this. Okay, so if I just mash the buttons and then I let go, let's see if this works. Whoa, let's not crash. I just mash the buttons and I let go. You can see that we've stacked a few moves. And the reason we do that is because of, if you've ever played the game of Snake, you see, like literally in this scenario, right? Like now I just want to go right down, for example, like immediately right and then immediately down. And then I can just queue down after right. So I just press right down. And then I've queued it. So like if we didn't do something like this, maybe we wouldn't be able to get both of them in. But actually, now that I think about it, that would probably work still. I don't know. Maybe you have some opinion about that. I mean, what wouldn't work is this sort of stacking. But then again, this stacking isn't necessarily super useful, I assume. But anyways, let's get back to the code. That was the original intention of why I did it as a list. So yeah, that's enqueue. So we've talked about enqueue, we've talked about next, we've talked about initial state, and I guess what we should do now is just talk about, well, first let's talk about these. So the next state is computed from the old state, right? And rows, when we do prop rows and prop calls, as we looked at in the other implementation, that just equates to the same value. Like we just say, this value is whatever the old value was. But however, next moves, let's actually look at next moves, right? So let's search for const next moves, right? And what this does is that it says, okay, it takes some state, and remember, so what it does, the intention is that it takes the whole state, but the intention is that it should produce only the list of moves, right? So it takes the whole and it produces the part. So we take the state and then we say, okay, state.moves.length is greater than 1. So we say, if we have more moves than 1, then we should drop the first move, right? So drop first is a function that I've defined here in the base. Drop first, which is, I mean, it's trivial. We just call a slice on an array, slice and then pass 1. But I just did this to make it more readable, right? Because now we can actually like very easily see what it does. So we say drop the first from state moves, or if the length of the moves list is not greater than 0, right? So if we have only a single move left, then it will simply be state.moves. So what this means is that if we have more than one move, we will drop the first move because we've used it. Like in the next state, we won't have we won't have the first move left because we've now used it. But if we have only a single move, then we shouldn't do that because we want to keep repeating that move, right? That's how we're achieving this effect where it just keeps moving right. I mean, I'm not touching anything, but it just keeps moving to the right. So that's because we keep that in. And of course, let me just quickly mention again that you can, using functional programming, you can make a lot of things point free, point 1, and point 2. I've also kind of mixed this sort of object-oriented dot syntax with this function syntax where you truly have a function and then pass the data. And I'm a bit disappointed about myself for doing that, but anyways, I mean, I just figured let's stay pragmatic. But probably like here we should do something like this, like length of state.moves, because this dot syntax is fine because this is purely data, but then length is a function on that. But this is a sort of give and take. I mean, I don't think we're going to be able to get away from this anytime soon in JavaScript, because like maybe my terminology is a bit shaky here, but if you've tried Haskell, for example, like you have ad hoc polymorphism and you have parametric polymorphism, and ad hoc polymorphism is kind of like polymorphism in object-oriented programming. And so the thing in Haskell is that you can actually define a length function that takes some data and then does different things depending on the type of that data. That's a bit tricky in a language such as JavaScript, because we don't have ad hoc polymorphism in that way. The way we achieve ad hoc polymorphism is through object-oriented polymorphism, is by saying that length is a function that exists on an object. And in a dynamically typed language such as JavaScript, we say, well, everything is a duck type, right? Like if it quacks, it's a duck. So everything that responds to length is lengthable, but which implementation of length you get depends on which object you call the method length on. So I mean, it's a give and take. Like we probably have to mix these two types of syntax before we have facilities for ad hoc polymorphism that looks a bit more like something like Haskell in JavaScript, which probably we maybe won't, because maybe I'm not realizing how difficult that would be to implement in a dynamic language. But anyways, now we're way out of the zone, so let's get back into this game. But I just wanted to mention that I'm completely aware that it's not superb. Anyways, how do we compute the next position of the apple? Well, if this is when we get to this will eat that we talked about, right? Like if the snake will eat the apple given the current state, then we need to spawn a new position, and that's when we're using this R&D pos that we talked about. That is the function in this snake library that is impure. Or actually, I mean, then next apple becomes impure because it's making use of an impure function, but whatever. So if the snake, given the current state, will eat the apple, then we need to spawn a new position for the apple based on the current state. If it's not, right? If the snake is not going to eat the apple, then the apple will maintain its position. The new position for the apple will be the same. So let's actually, for the fun of it, I mean, let's actually do the same thing in both of these cases, right? Like we have the cases where it will eat and we have the case where it won't eat. So let's change the won't eat case to also spawning a new apple at a random position. And then if we refresh this and run this again, you can see that it's absolute and total madness, right? Because now we have the apple is sort of respawning at new locations regardless of whether we're eating the apple or not. So actually, I mean, I don't know the probabilities here, but it's probably, I have no idea whether it's higher or lower, but like it's a very tricky game to play. So this is surely not what we want. And then also for the fun of it, let's try the other thing. Like let's say instead of when we eat an apple that's spawning it at a random position, let's just spawn it at the same position. Let's say that the new position of the apple is the same as the old position of the apple, regardless of whether we ate it or not. Then we can see that what happens is that we don't spawn a new apple, right? The game works fine, but we can just like hands off and then just leave it like this because we're just going to eat all the apples until we crash. Actually, it's probably still tricky again because the snake will take up all the screen and then it's going to be tricky to eat the apple. But anyways, I mean, clearly what we want is a random position. So what we want is this, like we spawn a new position when we eat the apple. And again, there's like some of these things are very easy to think about when you have immutability. Like I would imagine that going back and forth between these two changes would be more difficult if you had. It would potentially be more difficult if you had mutable state, depending on how you had structured your code, clearly. Next thing, let's move to next head, right? So next head, well, let's think about it this way. We have next snake and we have next head. So maybe these should be in the other direction, right? So, and I think next snake was called in the next method here, right? So yeah, so we're saying snake is equal to next snake. So if we go back to next snake here, and next snake makes use of next head. So let's actually talk about next snake first. So let's first think about the snake, right? Like look at this. Like let's actually grab one more apple here. So now we're a snake of 3 dots, right? If you look at it, now we're 4. But so the snake is a list of positions, and now it's a list with 4 elements that each have positions. And I think, if I'm not mistaken, yeah, we'll have to see. Either the first element or the last element in the list is the head of the snake. So what we do is that we just, when we need to move the snake, we remove one element in the end, and then we add one element in the beginning. And when we eat, right, think about it, look at what happens when we eat. Then the snake is prolonged. So what happens is that we add one in the front, but we don't remove one in the end. Or I shouldn't say we add one in the front. What I mean is we do compute the next position of the head, but we don't remove one from the tail, right? So we have the snake here, and then we're saying, okay, if you're not eating, we should just take the snake and move it here. But if you're eating, then we should take the head and move it here, but the tail should be fixed. We should not remove anything from the end, because it's this removing that gives the appearance of it moving, right? Because it's actually that we remove this thing. Maybe it's easier maybe if we just think about 1 dot, right? Like if you have one dot, like one snake head, then what happens when we're not eating is that we're just saying, okay, remove this, boop, and make another one here. And that gives the appearance of moving, right? Choop, and then choop, and so forth. But if we're eating, we're saying create the new one, right? You have one here, create the new one, choop, but don't remove this one. Right? So we give the appearance of prolongation and not of extension and not of moving. Of course, of moving as well. But anyways, so that's the way that we structured that. By the way, I mean, I tried this in multiple different approaches. I also try, I mean, it's an interesting game because you can also approach it by building up a grid and then sort of making operations on that grid. So like you have a 2x2 array, like a matrix. But anyways, maybe if you try out the solution along those lines, maybe again shoot something in the comments that would be interesting to look at. So, to compute the next snake, what do we do? Well, what we do is that we have two ifs, we have two nested ifs. We say, okay, if the snake will crash, right, given the current state, given the current direction, given the current world, if in the next state that we are now computing, will the snake crash or not? Like, if it will crash, then the next snake is going to be an empty array. Then we're going back to this sort of initial state thing. We're saying, let's go back, the snake is an empty array. However, if the snake won't crash, we do any of these things. And if it won't crash, we're asking this. Well, is it so that the snake is eating? Because if it's eating, then what we want to do is just that we want to add the next head. We want to compute the position of the next head, like we did here with the hands, right? Like we have the snake here, and we want to add the snake here, or we want to move it here, right? And if it's eating, we just want to compute this new position, and then we want to concat that into the current, or with the current snake. However, if it's not eating, then we need to move it, or we need to give the appearance of moving. That means we can't just compute the new position, but we also need to drop the last position. So we need to remove something from the end. And let's just think about whether it's in the head or not. So what we're doing is that we're saying that the head is an array, and then we concat that with the old snake. Yeah, so what we're doing is that we're adding into the beginning, right? So we're not, it's not that we're pushing in positions into the end of the snake, but it's more like we're adding at index 0, and then we're shifting all of the other ones backwards. So I haven't at all thought about performance and efficiency, but I mean, clearly there are probably multiple ways you could improve this code. But so that's what happens when the snake is eating. We are adding a new head, but we're not removing the tail. And if it's not eating, we're adding a new head, and we are removing the tail. So actually, I mean, if we remove this drop last, just to try this out, right? Then we're saying it's going to get longer all the time. So if we run this now, you can see just like it's never ending. Like it doesn't matter if we eat or not, the snake is just growing and growing. And yeah, that was tricky for me to handle. But as you can see, right, like the snake just keeps on growing and growing and growing. Again, like a trivial thing to change. But we go back to actually dropping the last. And of course, if we did drop last here as well, just to be exhaustive, let's try that as well. That would mean that even if we are collecting apples, nothing happens. Like the snake isn't actually prolonged. So of course, what we want is that, like this. Okay, that's the next snake. But then, okay, as we were saying, next snake makes use of next head. So the question is, how do we compute the next position? And that's actually pretty interesting, right? So let's look at next head. So again, next head, the structure is that it takes a state and it produces a single position, right? So think about it. I mean, next snake takes a state and produces a list of snake positions. Next head takes the full state and produces a single position that represents the head of the snake. And what it does is that it too has to ask an if question. And the if question that it asks is that, do we currently have a snake or not, right? Like if the length is 0, like if you look here, right? As we talked about in next snake, of course, when we crash, we completely wipe out the snake so that we don't have a snake. So when we compute the next head, it might be that we're trying to compute the next head from no snake at all. So this is why we're asking, is the length 0? Because if it is 0, then this we want to, is like the default start position. Maybe I should have had that as a comment or something like that. Actually, if you look at it, if we refresh here, you can see that this supposedly is 2, 2. Actually, let's think about it. That means so x3 and y3 if you start from 1. So this is why, I mean, maybe one would assume that it's here, but actually this is 1, 1 because this is 0, 0. So here it's 0, 0, 1, 1, and then 2, 2. So yeah, we start at 2, 2 all the time. And that's essentially because when the length of the snake is 0, then we spawn at 2, 2. And again, I mean, we could do R&D, let's say R&D pause given the state. Yeah. that should work as well. Then we are starting at random positions. We're always starting going east, but now we're spawning it at random positions. We're spawning the snake at random positions. But I figured this makes sense. I mean, it's kind of nice to start from 2, 2. And then also it's obvious that you've crashed. So that's what happens if the snake is 0, like if it's the initial case. But if we do have a snake, like if the length of the snake is currently longer than 0, what do? Well, this I found pretty cool. We create a new position that has an X and then that has a Y, of course. And what we do is that we take think about how these two look very much the same, right? Like X and Y is essentially the same thing. But what we do is that we say the X position is the current X position of the snake, of the current head of the snake, right? What's in the 0th position, plus the X of this move that we've stacked, the next move that we want to grab. So the move that is pending, the move that we're supposed to execute now. And remember, like the moves that we can have are any of these: north, south, east, west. So if we have east stacked, right, as in the default case, then X will be 1. So what we're saying here is that we're saying state.snake. So we're taking the snake position, and supposedly if we start at 2, as we've defined as the sort of default start position here. So if we start at 2 and then we say plus and we add 1 because east is 1, so the default direction is 1, then we get 3, right? Because the current head is at 2, 2, or if we only think about the X position, the current head is at X2, and then if we add 1, we end up in X3, right? And that's actually the next head. Now the question then, and of course maybe what we should mention is that this of course works for negative as well. So if the position is 2 and you add -1, then you get 1 because you're moving in the other direction. And the reason then that we have this mod thing is that we're making use of the modulus operator. So actually, I mean, in the best of worlds, I wouldn't have had to write that. I should have been able to write something like, let's think about this. So the same calculation mod state.calls. That's the way I wanted to use it. Like we want to use the mod operator, but apparently the modulus operator in JavaScript behaves differently than I had expected in regards to negative numbers. But think about it, the reason we use modulus here is that because we want to have this wrapping effect, right? Like notice how when we go out of the right end of the screen, like it's a torus, right? We go out on the right end of the screen and we show up on the left end. And similarly, if we go out on the left end, we show up on the right end. And that modulus operator is actually everything that's needed to implement that. Because what we're saying is that if the grid, let's say that the grid is 12, right? Like let's think of a clock. So if, I'm not sure if I can do mod here actually. So if I do 10, yeah, I can't. Okay, so let's do it in Google. So if we do 10 modulo 12, for example, we get 10 because, so let me be more clear. So if 12 is the width of the grid, and we're talking about the X position, let's say. So the number of columns that we have to work with is 12. And that means that 0 is an okay position, 11 is an okay position, 12 is not an okay position. So if we do 0, 12, modulo 12, that means that it's the 0th position. So what I mean is that 12 is the size of the grid, and 0 is the position that we want to position the next head in if we don't think about this wrapping around, right? Like then you could say position 316, right? Like even if you have a grid of 12. Actually, I mean, we could do that. That's the point of modulo. So if we do 316 modulo 12, that means that if you try to move to position 316, you should actually be at position 4 because you've wrapped around, you've looped around multiple times. But if we just think about the edge cases, right? Like 0 yields 0, so that means the 0th position. So that means we're not changing 0. And if you do 12, you also get 0 because 12 modulo 12, like 12 divided by 12, gives a remainder of 0. So that also puts you back in position 0, which makes sense because we're saying it's 0 indexed, right? So because we have the 0 index, the max index is 11. So when we try to go to 12, we should wrap around back to 0. So maybe I'm not making a superb job of explaining this, but every number then between 0 and 11 inclusive will be the number that we pass. So if we pass 2, we get 2. If we pass 3, we get 3. If we pass 4, we get 4, and so forth. But if we pass higher numbers, which happens when we are at position 11 and we pass 1, right? So, or we add 1, right? So this is more like the scenario that we have. We are at position 11, we pass 1, and then we do modulo 12 of that. So that gives us 12 that we do modulo 12 on. And that gives us 0. That makes us wrap around back. And let's jump into Node quickly and look at this. So actually, I should have done this in Node from the beginning. so 10 modulo 12 gives us 10, right? But 12 modulo 12 gives us 0, which wraps us around back. Similarly, 13 then gives us 1, but this is a case where that we're never seeing. However, what I would want is that -1 should also wrap. So -1 should put us in the other end of the 12, and that's the way I was expecting that that modulo was behaving. So let's see, can we require the base library from here? So let's try to require base. Oh, sorry, base equals require. Oh, sorry, because now I declared it twice, but messed up. So let's restart, jump back into Node. So let's require the base library. Wow, sorry, I'm such a confused person. So let's jump into Node and let's say const base is equal to require from the current directory the file called base. Let's just be specific and say .js. Right, and that works. Then we have the base library. And base, I mean the base library that we've defined in this project. And base has the function mod, right? So this mod, however, works differently. It works the same if you pass 10 and 12 again. Then you get, no, sorry, it's the, okay, sorry, for other reasons I did it in the other order. So here I pass, so this, if I pass it this way, I mean 10 modulo 12. Then we get 10. If I pass 12, we wrap around to 0, similarly for 13, but again, we never end up in that scenario. But now if I pass -1, we wrap around in the other direction and end up at 11, and modulo 2, and so forth. So yeah, and that's a different implementation of modulo, and I think I left a comment here. Yeah, I left a comment here to a link that you can check out if you're interested in the source. I think that came from a Stack Overflow post or something like that. So anyways, that was one of these moments where you go like, excellent. Like it's awesome when math can make problems that seem a bit tricky to solve in programming, but math makes them trivial. Those are the good days, right? But anyways, so that's why we do modulo here. So what we're saying is that this is the raw quotation marks, the raw new position, and then we say take that position and do modulo of the size of the rows or the calls, depending on which one we're working with, so that we wrap around. But yeah, that's next head, and so next snake is based on that next head essentially. And yeah, the randomness here we've talked about, the initial state we've talked about, next we've talked about, and Q we've talked about. Oh my god, have we actually talked about everything now? So yeah, I think we've talked about everything, and that sort of covers it in getting to the point where the snake game is operating something like this, because we also looked at the web HTML and JS file, and of course, I mean, I also have this web.css file with just some basic styling in order to make this look a bit prettier. I mean, if we remove, I'm not even sure, like if I remove this stuff, it looks like this, right? I've actually zoomed in. So this is what we actually draw on the canvas, but this is just some basic styling that I added in order to make it look like this. But yeah, that's it. Before we wrap this up, let's actually also look at the CLI. So the command line interface. So I'm opening up CLI.js.